Okay, so acid and bases come in pairs, and we call these pairs conjugate acid-base pairs. Now, the word conjugate basically just means closely related or next to, you know. So a conjugate base of an acid, right? Conjugate base of an acid is the remainder of the original acid after the acid has donated a proton, right? Whereas the conjugate acid of a base is going to be what you get when that base has gone and accepted a proton. So here we've got a example where ethanoic acid reacts with water, right? Now the ethanoic acid donates a hydrogen to the H2O, right? So the H plus is going to go to the H2O, right? So that the H2O can go form the H3O plus. So in this instance here, this thing here, the ethanoic acid is acting as an acid. And as a result of its actions, it's acting like an acid, it has gone and lost a proton, a hydrogen ion, and so has formed this thing here. Now this here we would call the conjugate base. I'm just going to call it base 1 and this acid 1. And the reason we would call it the conjugate base is, well, if you're going to go in the other direction again, to take the ethanoate ion and turn it into the ethanoic acid, the ethanoate ion actually has to go and receive or accept a proton, which means that it would be acting as a base. Now here the water accepted a proton in order to form a hydronium ion. So the water acted as a base, I'm going to call it B2, right? And then for the hydronium ion to go back and form water again, well, it would have to give up the hydrogen ion that it just gained. So we're going to call this acid 2. Okay, and those then are going to be our conjugate acid-base pairs, right? So the H2O and the H3O plus is a conjugate acid-base pair, where the H2O is the base and the hydronium is the conjugate acid, right? And then the ethanoic acid and the ethanoate ion is going to be the other conjugate acid-base pair, where the ethanoic acid is the acid, and the ethanoate ion is the conjugate base, right? So what you'll notice here is, because it's about, you know, what's left when you donate a proton or what you get when you receive a proton, well, the difference between the conjugate acids and bases is going to be a single proton. So you can see here that that proton is the difference, or here that proton is going to be the difference between the conjugates. Okay. Right, so let's look at a quick example here. And in fact, what I'd like you to do is pause the video here and see if you can identify which the conjugate acids and bases are going to be. Okay, fantastic. I'm glad that you gave that a try. So let's see what the reality is here. Now, we can kind of like link these up already, because it's not too difficult to identify which ones differ by a single proton, right? So you can see that HNO3 and NO3 negative, well, the difference is 1H, whereas H2O and H3O plus, or hydronium, well, that's something we've kind of already seen. So for HNO3 nitric acid to become nitrate, well, it has to give away a proton, right? So we're going to call this acid 1, and then its conjugate base is the nitrate ion. And then the H2O must be receiving, and so I'm going to call this base 2, and so its conjugate acid is the hydronium ion. Now note, you're always going to have one of the acids and one of the bases on the left-hand side, and one of the acids and one of the bases on the right-hand side. If you've got two acids on the left and two bases on the right, as in on the product side, well, then something has gone wrong, because how can you have two things that gave away their protons? Because, you know, who's receiving? For every gift, there must be somebody who's receiving. Otherwise, it's not a gift at all. Okay, so then again here we've got the NH3 and the NH4 plus, the ammonium, and then H2O and OH negative. Now here for NH3 to form ammonium, it has to accept a proton because it goes from 3 hydrogen ions to 3 hydrogens to 4 hydrogens. So this is now going to be base 1, and this NH4 plus is going to be acid 1. The ammonium is acid 1, right? So the ammonium is the conjugate acid of the base ammonia. But then the H2O actually gave away a proton to form OH negative, and so here the H2O is acting as an acid, and the hydroxide would then be the conjugate base. Okay, so something very interesting here. Notice that this water in this reaction acted as a base, but this water here in this reaction acted as an acid, right? So when you have a substance that is able to act as an acid or as a base, in other words, it can donate protons or it can receive protons, that substance is known as an amphiolite. Okay, an amphiolite or an amphiprotic substance. Okay, so it's kind of easy to remember this if you think about an amphibian, right? So what on earth is an amphibian? Well, it's something that can live both on water and on land, right? So it does it both. So an amphiolite or an amphiprotic substance is that thing that does it both. It can act as an acid or as a base. Okay, so when we have acids, our acids can either be defined as being monoprotic or polyprotic, right? So polyprotic is going to be these here, and poly is just a way of saying more than one, right? And protic is just going to refer to those protons that we've spoken of. In other words, the hydrogen ions that can be given away if we're talking about acids, right? So a monoprotic acid only has the one proton to donate, whereas a diprotic acid has 2 protons to donate. So that's, for example, going to be sulfuric acid. And then a triprotic acid would have 3 protons to donate, like phosphoric acid. Okay, now something interesting to note here is that ethanoic acid is one that is often confused because ethanoic acid is actually monoprotic. Okay, so this is monoprotic, and you might be like, okay, but I count 1, 2, 3, and then 4. So you count 4 hydrogens, so why can't it give away those hydrogens? Well, the H's that are bonded to the C are basically just not up for grabs. So from your organic chemistry, you might know that the shape of this molecule is going to be like this, the structural formula, and it's only this hydrogen that is bonded to the oxygen that can actually be donated under normal circumstances. These H's here that are bonded to the carbon, they are stuck in place. They're not going to come and go due to acid-base reactions. Okay, so those are polyprotic acids.